At Network Rail, we're responsible for over 20,000 miles of track, and that means over 40,000 miles of rail. Rail has many advantages over roads. It's self-steering and faster. It's got a higher loading capacity, and most of all, it's safer. 15 times safer than travelling by car. And one of the main reasons it's so safe is because our maintenance teams and engineers put a huge amount of work and care into looking after it. The type of material we choose to make our standard rail from is very important and highly specified. It's a 0.6% carbon steel with other alloying additions to increase its strength and hardness. It's a high performance material and as hard as a typical drill bit. 99% of our rail is made by Tata Steel in their huge steelworks in Scunthorpe. As a guide to the scale of the operation, the building containing the rail production line is over a mile long. The rail production process begins with 7.5 metre long blocks of steel called blooms, weighing 6.5 tonnes. These blooms are heated in a furnace to 1240 degrees centigrade to make the steel behave plastically and be capable of being shaped. The red-hot blooms are cleaned and descaled and then moved through the production line. Computer-controlled machinery squeezes, rolls and manipulates the blooms into a new form. In less than 10 minutes, the original bloom has a completely new cross-section profile and has been transformed from 7.5 metres to just over 108 metres in length. The rails are then pre-bent while still hot to counter the bending that occurs as they cool. Once cooled, the rails are straightened and trimmed and then passed through a complex computer-controlled NDT process to look at their profile, internal and surface quality using UV, lasers, ultrasonics and eddy currents. The tests ensure that every rail leaves the site free from defects. At Network Rail, we want the longest rails that we can practically deliver. The fewer joins, the stronger the rail. The longest rail that Tata Steel currently supplies to us is 108 metres long. The two rails are flash butt welded together to produce a 216 metres string. This is the practical limit of what we can deliver to track. Finally, the finished rails are loaded onto a delivery train. The rails are flexible enough to negotiate bends in the line and make their journey direct to the location where they are required. The standard of rail produced by Tata Steel is very high. But even the best rails won't last forever.
My name is Brian Whitney. I'm the Principal Track Engineer for Network Rail. Part of my job is to understand how the degradation of rail occurs, how quickly it happens, where it happens, and how to mitigate against it. There's four main types of degradation we see with rail. There's fatigue damage on the surface and internally within the rail. There is wear, both on the head and side wear. There is also plastic deformation of the rail and a loss of section due to corrosion. There's a few examples of rail we have here. This sample here shows a fatigue crack which is initiated from the surface of the rail. It's caused by the repeated passage of wheels over the surface, which will initiate small cracks, and then through fatigue this will grow progressively over a long period of time. The discoloration and classic markings you can see here are a result of the surface becoming oxidised and corroded where it becomes exposed to the elements. Surface damage and rolling contact fatigue is our biggest cause of problems. It accounts for something like 50 to 60% of all defects we remove from track each year. Other forms of fatigue that we see, here we have a large star crack which is originated from the bolt hole at a rail end. Equally, these are defects we need to manage. If they're allowed to go to failure, can result in a piece of the railhead becoming detached. Plastic deformation is another thing we see where the rails degrade. This is where the rails are physically deformed. They are spread, the rail steel itself is distorted and deformed under traffic. You can see the start of a small split within the middle of the web. These will propagate under traffic if not managed. They will grow to a larger size, the split will open up, and in extreme cases can result in a piece of the rail becoming detached. Most of our defects of this type occur in older rails where there are either inclusions or impurities within the rail steel which form a point of weakness which under repeated loading will cause the rail to fail. Another type of degradation is corrosion. Here we have an example of a rail removed from an aggressive environment where the foot of the rail is corroded away, a large amount of material has been lost. This will result in rail failure if the rail is not removed in good time. Aggressive areas are where we would have exposure to water or perhaps the sea on salt water. Level crossings are particularly bad where we have a lot of water from the road, and also during winter salt is applied to the road which causes a significant increase in the rate of corrosion in those locations. And finally, we have to deal with wear. This can be either vertical wear on the top of the rail or side wear you can see here from the side of the rail where the wheel wears the rail away.
One of the most important ways we manage rail is through inspection. At Network Rail, we use a fleet of monitoring trains to check on the condition of our track. Monitoring vehicles allow us to cover large quantities of rail miles in regular cycles. But in complex switch and crossing layouts, we still need to inspect on foot using portable kit.
This piece of equipment here is a Sperry roller search unit, also known as a walking stick. This is used by our ultrasonic operators who carry out a large amount of pedestrian testing in areas where we can't use vehicles to test, or in areas in lower category routes where we don't program the vehicles. The ultrasonic equipment here contains the Sperry roller search unit. This contains 9 probes which are used to scan the head and web of the rail, the floor detector which provides the signal and response and is used to detect any defects internally in the rail. This is contained in a walking stick to make it easy to push along the rail to ensure the stick stays aligned with the rail to carry out the necessary inspections. The inspection processes that we use today, the frequencies and the techniques and technologies that we use have been developed to minimise the risk of a rail breaking, to find defects in sufficient time that we can plan their remediation. If this isn't carried out at the right frequencies, then we can end up potentially with a catastrophic accident similar to what happened in 2000 where the train derailed because of a defective rail at Hatfield.
Following inspection, the next most important part of rail management is preventative maintenance, and the principal means of preventative maintenance are grinding and lubrication. Grinding is carried out on our main lines on a regular cyclic basis. It maintains the correct shape of the rail, removes small surface imperfections, and reduces the stresses that lead to fatigue damage in the surface of the rail. We use lubrication to minimize rail wear. Track-based lubrication equipment deposits a small bead of grease onto the wheel, which is then carried around the outside bend of a curve. Lubrication is used on most tight curves on the network to reduce rail wear and the premature replacement of the rail. Eventually, however, it will be necessary to replace the rail. The primary reasons are the number or severity of defects, wear or corrosion. Some rail can last up to 40 years if on a straight piece of track, but on the curves of a high-speed line, or where the rail is affected by road salting, the lifespan can be reduced to less than a year. Typically, if a relatively short section of rail needs to be replaced, this will be done at night to minimise the disruption to traffic. In this instance, a corroded level crossing rail is being removed and replaced. The defective rail is cut out and then removed from the site using a road rail vehicle. Once clear, a replacement section which has been cut to the required length is brought in and lowered into place. This will be attached to the existing line using an aluminothermic weld. First, the rail is clamped and pulled into position, and a mould assembled around the two rail ends to be joined. The rail ends are heated before welding to prevent the rail steel becoming brittle if it is allowed to cool too quickly. A crucible is placed on the mould. It contains iron oxide with specific alloying elements and volatile aluminium powder, which causes a chemical reaction that reduces the iron oxide into steel. The chemical reaction generates a huge amount of heat that melts the constituents to form liquid steel, which pours into the mould, fusing the rails together. The mould and excess weld metal is removed while it is still hot. The stripped weld is then profiled to exactly match the rail profile and produce a smooth finish. Following inspection, the new level crossing rail is ready to be used as part of the network.
The rail management engineer continues to face a significant challenge. Modern expectations for 24/7 operation, modern vehicles, whilst safer and more comfortable, are often heavier. These all result in great amounts of rail damage. One of the ways we can help combat rail damage and deterioration is the development of new materials. A number of processes have been employed to produce traditionally harder and harder rail steels to reduce wear. Recently, we've worked with Tata to engineer a new steel which provides not only a wear resistance but also a resistance to fatigue damage. This material, HP, we've just started installation in track and utilises some clever metallurgical and chemical alloying additions to produce a strong premium grade rail steel without the need for expensive heat treatment. This provides us with a cheaper premium rail steel with a similar performance to some of the more expensive heat treated steels currently available.
Careful management of materials, their specification, production, maintenance and replacement is a crucial part of rail engineering. It allows us to maintain progress, to keep trains running safely and efficiently, no matter what the demands of traffic, line speed or location.